All right, welcome back. We're Nature in Code and we're in chapter 3, and we're just about to finish our coin tossing example. So in the last lecture, we developed this code here that basically throws a coin 10 times if it comes up heads, which happens 50% of the case. So if math random is smaller or equal to 0.25, then we'll increase this heads variable by 1, else we'll increase the tails variable by 1, and then in the end we can output the number of heads and the number of tails, and that gives us precisely these outcomes here, the sort of 10 times tossing of a coin. Oh, look here, we actually have 1 heads and 9 tails. That's sufficiently rare. Nice. All right. So what we want to do, though, is we want to use JavaScript and show that if we throw 10 coins, or we flip a coin 10 times, then we will get 2 tails and 8 heads in 4.39% of the cases. So we'll have to do this many, many times. And so I'm going to wrap this here in a function. So I'm going to call this function throw coin. And I'm going to wrap this block here into this function. And I'm going to end the function right here. And I'm going to get rid of the console log statement here. So now we essentially just took that code here and we wrapped it into a function that we call throw coin. So these are now local variables. All right, so I can now just call throw coin here, and this function would get executed, and heads and tails would come up, however many times they will come up. So now I can write a loop here that calls this function many, many times. However, I need to know whether for each in each case, for each time when this function was called, whether it actually returns or whether the coins came up in such a way that there were 2 tails and 8 heads. So this is something I'll have to let the function caller know when the function returns. So what I'm going to do here is the following. I'm basically going to say, all right, so if, oops, I need to click here, if tails equals 2, or alternatively, and that would be the same thing, of course, if heads equals 8, then this function will return true. And we'll talk about this in a second. If that's not the case, so if heads isn't equal to 8, then we'll return false. Okay, and here I just made a capital mistake. And it's actually great that I made this mistake because I want you to be aware of it. This should be a double equal, oops, like this. And we'll talk about this in a second, okay? But this is now, so you saw up here the operator that you would use for smaller than. For greater than, you would simply use this one. If you want to compare 2 values in terms of their equality, you can use this double equal. Now there's also a triple equal that a lot of people prefer. For the purpose of this course, we're good enough with the double equal. We'll talk about this in a lecture further down the road. So the double equal compares the values of these 2, of the variable here and this numerical value here. So I just wanted you to be aware, don't do this, okay? Because you are effectively assigning a new value to heads. You're not really testing for equality. For that, you need to have at least 2 equal signs. All right. Now, what does the function return? So the function returns true or false. So this is now a third type that we discover in JavaScript. We had strings before. Remember, strings are basically just sequences of characters like this, hello world, and we put them in quotes, and we do this so that we can differentiate the string 100 from the numerical value 100. Okay, this has no intrinsic meaning. It's just a 1 and a character 1, character 0, character 0. This, on the other hand, means 100 as a numerical value. And now we have this third type other than numbers and strings, and those are called Boolean values. Okay, in the Boolean type, there are only two values. It's either true or false, and that's the only correct way to spell it in JavaScript. So basically now we can say, okay, if heads equals 8, then we return true. Otherwise, the function will return false. And now when we call the function, we can test for that. So we can now have a loop. We can set up a loop that calls throw coin many times. Actually, you know, let me call this throw coins, because we're really we're throwing multiple coins here. Okay, and so the way I'm going to do this is I'm going to say, well, first of all, again, I'm going to define how many repeats I want. And I'm going to use a lot here. Let's say, well, let me start with 100,000. Okay, we can always increase it later. Now I would like to count how often I throw 2 tails, and as we now know, I will know this because I have this return value here, and if this function returns true, I know I will have thrown 2 tails and 8 heads. So I need to count how often that happens, and I'm just going to set up a variable here called counter. Okay, so now I am going to define a loop once again, and this should be pretty standard by now. So I smaller than whatever we have here in repeats, and then of course I need to increment the variable I by 1. All right. So let me call this function, and let me save whatever this function returns in a special variable here. I'm going to call it desired outcome, because it's the desired outcome if there are 8 heads and 2 tails. So I'm going to just write it like this, very simple. Okay. Oops. So throw coins is called. It either returns true or false. Whatever it returns will be stored in this variable here. And now I can say if desired outcome, then I'm going to increase the counter by 1. Okay. So there's nothing I need to do in the other if the desired outcome isn't true. And by the way, you could of course write if desired outcome equals true. This is just a shortcut. All of these conditions evaluate to either true or false. Up here, this one, you compare 2 numbers, but the result of this comparison is true if it's really true that mathrandom returns something that is smaller than or equal to 2.5, or it's false. So this is just a shortcut here if desired outcome is actually true. So if this, whatever is in here is true, then I add 1 to the counter. If you prefer this, you could write this if it's easier for you. But you might as well just write if desired outcome, because desired outcome will be a Boolean value, either true or false. All right, and so that's it. So now all we have to do is get rid of this down here, and instead basically write how often we would get 8 heads and 2 tails, and that of course is the number of times, so which we store in counter, this function has returned true relative to how often we did this. Counter repeats. And we could just go ahead and write something nice here. So getting 8 heads to tails. Okay. And then we'll have this thing here. And then finally, percent of the time. And you may have noticed this actually doesn't give me the percentage. This just gives me the fraction. So to get the percentage, I will need to multiply this by 100, and just making sure that we have the correct order here. So first divide counter by repeats and then multiply by 100 to get the actual percentage. All right, let's save this. Let's go over to the browser. Let's reload the page. Look at that. Getting 8 heads, 2 tails, 4.394% of the time. And if you recall from the last lecture, that's exactly what the binomial distribution would predict. We could reload this a couple of times, and you see there's now some uncertainty here around this value, some variance. In fact, it's still very fast, so I'm going to up this here by a factor of 10 to 1,000,000. Okay, let me save this. Now let me run this 1,000,000 times. So here now on my machines, there's already a little bit of a lag, and you can see there's still a little bit of variance around it, but most of the time I get 3.9 something. And this is actually now pretty far away, 3.8, just very close. Let me up it this one more time, okay, to 10 million repeats. Might take a couple of seconds now. 4.39, 4.39, reload again. 4.39. So it's very consistent now if you really go up to the maximum value that we can handle. Of course, we could handle 100 million as well. It would just take a minute or so, and that's not really necessary. All right, so this concludes this lecture. So we have just taken that whole throw coin example, we've encapsulated it into a function, and then we said, well, if the result is such that there are 8 heads, 2 tails, then we return true, otherwise we return false. And down here now, we basically call this method however million times we want to, and we count the number of times this function actually really returns true, which means we got 8 heads and 2 tails. And then we divide that by the number of times we call this function, which is stored here in repeats, and then we output the result of that. So if you followed this and if you understood all of this, then you're doing great, because this is now already pretty, well, I wouldn't necessarily say complex, but given that you might not have programmed in JavaScript or any other language just a few videos ago, this is now pretty sophisticated. I mean, you're using variables, you're using math, you're using random number generators, you're using functions, you're using control flow, if else, you're using iterations, loops, you're using Boolean values, numbers, and strings, and all of this to basically demonstrate that indeed, if you throw 10 coins, you would expect to get 8 heads and 2 tails 4.39% of the time. Of course, we're going to use this type of knowledge and this type of programming skill not to demonstrate something that is already established mathematically, but rather to run simulations of genetic evolution. But I hope this brings home the concept of math random, of this random number generator that will be truly essential in all of the code that will follow. So I introduced a number of concepts in these past few lectures, and in the next video, I'm just going to dig a little deeper with respect to conditions, with respect to control flow, and also talk a little bit about the types one more time, just to make sure we're solid on the technical aspects of everything. All right, see you in the next lecture.